Problem number 8. A mint produces 100,000 coins. Upon weighting some of them with a precise scale, officials find that the coins vary slightly in weight, with an independent uncertainty of 1%. About how many coins must be randomly sampled and weighted in order to determine the total weight of the coins with a 0.1% uncertainty. Assume there are no sources of systematic uncertainty. Solution for problem number 8. If we have independent uncertainties, we can use formula that uncertainty for total mass delta n equal square root from number of coins multiplied by uncertainty for one coin. Total mass equal number of coins multiplied by mass of coin. So we can just divide first formula by second formula, and we have this relation. In this formula we need uncertainty for total mass equal 0.1% or 0.001. Uncertainty for one coin is 0.01. So it means that combining all these expressions, we can find that number of coins equal 100. And this is answer D, and that was solution for problem number 8. Problem number 9. NASA trains astronauts to experience weightlessness with an airplane which flies at a parabolic arc with a constant acceleration g downward the ground. The plane can remain on this trajectory for at most 25 seconds due to the large change in altitude required. If instead of simulating weightlessness, NASA wanted to fly a trajectory that would simulate the gravitational acceleration of Mars, 3.7 meters per second square. For what length of the time can the plane simulate Mars gravity? Assume that the maximum change in altitude is the same for both trajectories. Solution for problem number 9. First, we can find what is the change of altitude. For that, we can use formula h equal 1/2 gt square. Here, total time is 25 seconds, but this is for trajectory up and down. So it means that for time we have to use half of this 25 seconds. So it means that total change of height is 766 meters. After that we can find which acceleration need to use airplane to simulate acceleration of gravity on Mars. That will be a equal g minus a0, where a0 it's gravitational acceleration on Mars. So that will be 6.1 meters per second square. And now we can count what is total time for motion up. That will be this expression. So it means that to move it up we need 15.8 seconds. And we have to double this time for motion up and down, which give us approximately 31.6 seconds. This answer is closest to answer B, 31 seconds. And that was a solution for problem number 9. Problem number 10. A uniform solid circular disk of mass m is on a flat, frictionless horizontal table. The center of mass of the disk is at rest and the disk is spinning with angular frequency omega 0. A stone modeled as a point object also of mass m is placed on the edge of the disk with zero initial velocity relative to the table. A rim built into the disk constrains the stone to slide with the friction along the disk's edge. After the stone stops sliding with respect to the disk, what is the angular frequency of rotation of the disk and the stone together? Solution for problem number 10. Here we can use angular momentum conservation. So we have angular momentum equal I0 multiplied by omega 0, where I0 for solid disk is 1/2 m r square. Now when we put this stone on the edge of this disk, we still have the same angular momentum, but now all construction rotates around common center of mass, which stay on a distance r/2 from the center of the disk. So it means that for this construction we need to count what is moment of inertia. For stone that will be m multiplied by r/2 square, and for disk that will be this expression. Here we use a parallel access theorem. So it means that the total moment of inertia for this system around the center of mass equal mr square. Now we can use angular momentum conservation. I multiplied by nu omega equal I0 multiplied by omega 0, and the final frequency will be omega 0/2, which is answer C, and that was solution for problem number 10.